This on and off network, I want to prevent. Just change. This Unilag network is, I don't think it's not stable. So let me use my data. So that's what I'm trying to do now. All right. My data is on, right? Okay.
Recording in progress.
All right. So I think this should be a better network. The earth as a heat engine. So that is what a caption that I can give to this topic. So the core concept now, Earth is a dynamic planet. Another thing I remember now, you guys, you missed this class last week. You missed this class last week. No information, nothing, but I just decided to just look the other way. Because of that now, we only have one more week, which is next week. So I might have to combine the two topics for next week. So, but let's just see how that pans out. So Earth is a dynamic planet, not because of surface processes alone, because what we are used to is this, what goes on at the surface, what we do as human, but because it's a massive complex heat engine, internal thermal energy is converted into mechanical work, that is movement, driving essentially all large-scale geological phenomena. So there are a lot of things happening within the Earth crust, the mantle, the core, and all that. Now, does this thing? How do they manifest? What do we see? We see it from plate tectonics. I remember we discussed it briefly in your year one. Volcanism, from volcanic eruption, earthquake, mountain building, and all that. And the generation of the magnetic field are all surface expression of this internal engine. This is what we see. So when you see volcanic eruption, it shows that a lot of things is happening within the subsurface. So we try to explore where the heat comes from, how it moves, how we measure it, how to deduce past temperature and all that, and the ultimately power and how it ultimately powers the planet. So probably might not cover everything, but at least do justice. Sources of heat or Earth's internal heat. There are two primary contributors to this heat. We have the primordial heat. These are the residual thermal energy from planetary accretion. Planets, as they add more layers, as we shed more of, and things like those things. And this has been as far as back 4.5 giga annum years. It has been as old as that. As the planets or planetesimal collides, these are the the smaller planetary bodies. As they collide, their kinetic energy was converted to heat. Additional heat come from the core formation events, where gravitational potential energy was released as dense ion sank. Then dense ion sank to the center. As dense ion sank to the center. Let me read that again. Let me say it again. Additional heat came from the core formation event. You know core now? You know how the core, how they are formed. In this case, we have gravitational potential energy were released, causing dense ion to sink to the center. Analogy is the leftover warmth from vigorously stirring a thick soup. You know what happened? When you stir a soup that is thick, now this time the soup is cold. You now stir it continuously. You see that there's it's warm up, it warms up. So as a result, it allows dissipation over billions of years. So this motion from the core causes heat. That is primordial heat. Then we have the radiogenic heat. The dormant present source of this kind of heat that means the heat that we derived, that the heat that we see now, present day, and it's about 80% of the total heat flow. So the heat that's generated these days, not from the core, not from the mantle, are the radiogenic heats. It's generated by the spontaneous reactive decay of isotopes in Earth's mantle and crust, not by motion as in primordial, but decay, disintegration. So these materials are uranium, thorium, and potassium. It could be uranium 238 or 235. This is important because these elements are geochemically incompatible, meaning that they are excluded from the core and concentrate in the silicate mantle and crust during planetary differentiation. Their continuous decay provides a long-term power source. So mechanism of heat transfer. Basically, we have the conduction, convection, and radiation. There could also be what we call the advection. Adversion. So, what is this thing? But mainly we have this. Heat moves from hot core to cooler surface via conduction. From here through energy, kinetic energy, contacting each other, which is dominant in the lithosphere. This is from the core to the top of the asthenosphere. So this conduction is a type of heat transfer that happens when you hold a metal spoon that is hot at one end. Later realize that the end that you hold that is cold will become hot. That is conduction because heats are conducted from the hot place to the cool place. So also in geology, heat conduction or heat conducts through solid rocks as well. Heat conducts through solid rocks. So the next one is convection. Large-scale transfer of heat by the physical movement of material itself. A hot, less dense material rises. A cool, dense material sinks, forming a convection cell, dominant in the ductile ionosphere and also the outer core. So that's where we have convection. So that shows that convections are basically in fluids. Energy transfer or movement through convection are basically when there are fluids, be it gas and liquid. So this liquid move from one end to the other. Example, boiling water or a lava lamp. The radiation. This does not need material to propagate. It's through electromagnetic wave. Most times you only see it within the crust, within the subsurface, but you see it basically outside the crust, within atmosphere, from the lithosphere out to the atmosphere. So that's why I say negligible inside the earth, but crucial for losing heat from the surface to space, from the surface to space, e.g., heat from the sun. So another way is that advection, which is heat flow is transfer. Let me do this. Adventure heat flow, which is the transfer of thermal energy through the bulk movement of liquid or material, transporting it from the location to another, just like what we have in conduction, really. Convection, sorry, not conduction, convection. So this is a schematic of how some of these heats are produced and transferred. So basically, this primordial heat is like 20%, while the radiogenic is about 80%. Other contribution is as small as this. And look at this example of the earth crust and how some of this, the percentage of this heat from one point to the other, be it at the core to the lower mantle, or the lower core, outer core, lower mantle, upper mantle, and the crust. You can see where we have adventure, where we have convection, and where we have conduction as well. So, like I said, you can see there's no radiation here because we are dealing within the earth crust. Radiation is outside. So, how do you measure its flow? Using the symbol Q, small letter Q. So the heat flow is the rate of heat energy transfer per unit area. It is fundamental, observable. It is this fundamental observable that tells us how vigorously Earth's engine is running. So, meaning that this heat flow, if for instance, if the Earth is very cool, meaning that the Earth is not moving, it's not in motion, there's no flow. But when it's hot, it shows that the Earth is really in motion. The conductive heat flow equals to Q, that is minus K times change in T divided by, the T dZ, where Q is the heat flow, K is thermal conductivity of the rock or the body or the material medium, while the thermal is the T dZ is the thermal gradient, which is the rate of temperature decrease with depth. How we measure it? Drill a borehole and measure temperature T at various depths to get the gradients. Retrieve rock sample and measure the thermal conductivity in the lab. Calculate Q. So global average is 87, but highly variable. So this is varies, but global average is this of heat temperature or heat flow. So when we have high heat flow, that is from 100 to 300, you can see it's very high here. And it is found around mid-ocean ridge, hot swelling mantle, volcanic arc rift. These are mid-ridge. If you remember this thing, when we spoke about regions that are volcanically active, where earthquake can occur, earthquake region and all that. Remember, we spoke about mid-ridge, a mid-ocean ridge rather. You can see heat flow is as high as 300. Megawatts per meter cube. So, and it could be low as less than 50. Old oceanic crusts, stable craters, that is ancient continental cores. So these are where you can find this. I think I decided to do a more steady explanation again on that topic of heat flow. That is what I've done here again, so that to give you a clearer understanding. You can see it introduces a core concept for understanding Earth thermal energy. Surface heat flow, which is surface heat flow. Think of Earth like a giant engine. Heat flow is the exhaust. or the signature that tells us how much activity is happening deep within our feet. How heat flow. In simple terms, heat flow is the amount of heat energy escaping from the Earth's interior through its surface. It is measured in milliwatts per square meter. Milliwatts. If it is capital M, that's mega. So milliwatts per square meter or per meter square, anyone. Is crucial. It's a crucial observable because we can't go into the center of the earth, but we can measure the heat that makes it to the surface to infer what is happening below. So you can see this is the expression, and these are what I have done. So I've explained those the term matter. So how do we measure it? Like I said earlier, it involves 3 steps: drill, we sink a borehole into the ground. So we measure, we lower thermometer to find the temperature at different depths to calculate the gradients. We bring raw back to the lab to measure their conductivity. That is K. That's how we get K. They multiply them together. That is K times the T dz. So, and you can see this also, I've explained this earlier. So let's move on. So this is just a schematic to show how it flow based on some measurement that I've done in the past around the globe. So let's look at this calculation. A borehole in continental crust reaches 3 kilometers deep or a depth of 3 kilometers. The temperature at the bottom is 90 degrees Celsius, while the surface is 15 degrees Celsius. The average conductivity K of the granitic rod that was brought out from the well is 2.5 watts per meter. Per meter for times the conductivity times K. Calculate the heat flow now. So this is the expression, this is the formula for conductivity. Calculate this flow. The gradient is, one is at the bottom is 90, at the surface is 15, so you subtract. So we have 75. Then change in the distance travel is 3 kilometers. So the difference is that 3 kilometers, that's 3,000 meters. So the T dz equals to 75 divided by 3,000 meters, which gives us this centigrade per, 30 degrees Celsius per meter, which is equals to 25 degrees Celsius per kilometer. Now, multiply this by the conductivity. You eventually have this. So this temperature, this is moderate, typical value for stable continental crust. So I think that is self-explanatory. So this is moderate because why did I say it's moderate? Because the average is 87 again. Yes, it's 7. So which is not up to the average. So it's still a bit on the low side. So geothermometry, reading the fossil thermometer. So what are we trying to do here? We're trying to say, how do we know the temperature at which a rock formed deep in the crust or in the mantle millions of years ago? You can see. How do we know the temperature? So we use geothermometers, mineral properties sensitive to formation temperature. So that means there are some minerals, there are some geological minerals that that are sensitive to temperature at which they are formed. So it shows that when you see those minerals, you can say that well, if the mineral is like this, that means the temperature at which they are formed is like this. So how do we do that? Through element partitioning. The distribution of certain elements between coexisting minerals is temperature dependent. So that means we try to take an element or a mineral and partition to separate it. Example, iron magnesium exchange between garnet and clinophyozine in mantle zeolites. I mean, xenolite, geology student, you know how to pronounce this very well. The conductivity, that is K, KD, this is K subscript D. That's partition coefficient, gives a precise formation temperature. Now, isotopic ratio, the fractionation of light isotope, oxygen 18 or oxygen 16 between minerals, mineral solveness, the composition of exhaust phases, e.g. in first part upon cooling. Application, reconstructing the thermal history of mountain belts, understanding the depth stroke temperature of magma generation, and constraining metamorphic conditions. Now, this sounds a bit cumbersome, right? Everything seems not to be that clear. So let's move. We now see that I've explained in bits. I've provided clear explanation here now. In the next two slides, I guess. Yes, in the next two slides. So now, geothermometry is essentially the science of looking at the rock and figuring out exactly how hot how hot it was when it first formed millions of years ago. Think of a mineral as fossil thermometer, meaning that that mineral is more or less like a thermometer because it gives us information about the temperature. So think of a mineral as fossil thermometer that freezes a specific temperature signature into the chemical structure, meaning that the temperature of formation, it freezes it. It gives that indication that because I'm like this, because this like this, because you have this kind of pattern, then it shows that the temperature is 120 degrees. Probably if the mineral shows a very dark color, it shows that the temperature is not high. If it shows a red color, it could show that the temperature is high. That is what this means. So by the time you now look at the chemical composition or whatever you see within that fossil, within that mineral or fossil material, you can say that the temperature at which it formed is this or that. Core concept: we can't travel back into time, like I said earlier, to stick a thermometer into the Earth's mantle. So we use geothermometer. Specific mineral property that change predictably based on formation temperature. By measuring these properties today, we can calculate the condition of the deep crust or mantle in the distant past. So key methods is reading the rocks. Geologists use three main chemical signatures to determine temperature at formation. So element partitioning, like I said earlier as well. This look at how different elements, e.g. iron and magnesium, distribute themselves between two different minerals that grew next to each other. And the rule is as temperature changes, elements prefer one mineral over the other in a mathematical, predictable way. Example, by looking at the iron magnesium exchange between garnet and the clinopyrozine, we can calculate the precise partition coefficient, KD, that translates directly to a formation temperature. The next one is isotopic ratios. This involves measuring the ratio of light isotopes, oxygen 16, oxygen 18, between different minerals.